Okay, happy for me to start?
Yep, so thanks everyone for coming. We've got, Rob Morton, who's been with us through COVID.
Too long.
Out of the office. Yeah. So it's actually been really nice though, and I will be sad when Rob will be very happy. I'll be really sad when Rob completes. We first started working together as grads, as consultants a long time ago. And so it's been really nice to work together again in a different context. But given I'm already late, I will hand over.
Okay, now just bear with me a moment while I... Does anybody else find these meeting rooms very confusing to operate and to get meetings going? It's just very strange. Maybe I'm doing it the wrong way. So I need to go in here and awesome. And okay, now hopefully everybody online can see, can't see my presenter view. That would be really bad if you could see that.
Yeah, it looks good to us.
Awesome. Phew, technology works. That's great. So welcome everybody. This is my completion seminar. Thank you for coming along. There will be no rotten tomatoes until the end, please. So my topic is hydrological threats to biodiversity in unregulated streams. Now, obviously, there's some big words in there, so I'm going to start with a couple of definitions of what exactly do I mean by some of these terms, and then I'm going to move into perhaps discuss a little bit about it's a bit more of a philosophical discussion about why would anybody study unregulated streams? What's the interest? And then I'll get into some of the cool technical stuff which we're all here to see. So let's start with the a couple of definitions. Hydrological threats to biodiversity in unregulated streams. So first of all, what do I mean by a hydrological threat to biodiversity? So just very quickly, this diagram is from a paper by David Dudgeon, and it's really talks about the different sources of, there's a lot of different threats to biodiversity in streams. What can affect the fish and the bugs and the frogs and the trees. There's a lot of different sources of that, and they tend to fall into these groups. We do love a Venn diagram, don't we? So there's things like pollution, which can affect water quality, land use change, which can affect water quality and physical habitat, invasive species, which is a direct effect on the biota itself, and there's flow regulation, which is a large infrastructure actually affecting the flow regime itself. And overlaid on top of that is just general issues of overexploitation and, of course, climate change, the ever-present climate change. So my research is specifically about flow regulation. It's about things which affect the flow regime. So I'm not going to delve into water quality or things that affect habitat. There's probably about a dozen PhDs in all of those topics. So I'm just going to confine it to flow regulation, things that affect the flow regime. Now, what do I mean by an unregulated stream? This is an aerial image of a little section of New South Wales. That's Blowering Dam, not too far from Canberra. The Tumut River is just downstream of Blowering Dam. Because there's a zonking great dam on the Tumut River, we call that regulated. So it doesn't, there some jurisdictions have a particular definition of regulated versus unregulated, which depends on the operation of the dam. I'm not interested in the operation. I'm just saying there's a large dam. It affects the flow regime. Therefore, the Tumut River is regulated. So that's a regulated stream. All these other streams you can see over here, they're all unregulated because there is no large extraction. There's no large dam. So my research is all about streams which don't have large dams and large extractions, and specifically looking at what's going on in those streams that could affect the biodiversity via the flow regime. Now, so what actually is the problem with unregulated streams? The reason I'm focusing on these little streams. If you're interested in what's going on in the Tumut River, if you go digging around in all the government reports, you're in luck, because there will be oodles of reports on what the flow regime looks like, ecological monitoring. There'll be lots of ecological monitoring. There'll be lots of flow monitoring. There'll be just so much information about the Tumut River and regulated streams like it. And if you delve into the scientific literature, there are literally thousands of papers about dams and how to manage waterways downstream of dams. If you're interested in the unregulated streams on the other side of that image, you're probably out of luck, because there's not going to be a whole lot of government reports. There's some monitoring, but not a lot. I think in that image, there's probably 2 streamflow gauges, and I don't know what the quality's like. There might be some ecological monitoring, but not nearly as much as a regulated stream. The reason for that emphasis on the regulated streams is because there's a big dam. There's a giant dam which affects the flow regime. And in the unregulated system, there is those streams there. There's no major dams, there's no major extractions to affect the regime. But is there nothing at all affecting the flow regime? Let's have a look. Oh, wrong mouse, this mouse. See if I can get a pointer. Oh yeah, just about. You can see these, this dark area in the center here. That dark area is in fact plantations. There's a lot of forestry goes on in this area. So that's plantations. You can see all the white patches here. These white patches they're actually netting for orchards. So there's things like apple trees and peach trees and cherries, that kind of thing. That's horticulture. Plantations and horticulture, because of the extraction, because they extract water out of the stream, they can affect the flow regime. So there's horticulture there. You'll just have to believe me that when you zoom into this image, there are bazillions of little tiny dams. I haven't checked the records, but there's likely to be small extractions. There's likely to be groundwater extractions. There are things going on in this catchment which can affect the flow regime. There is no one big piece of infrastructure. It's distributed. So these are distributed impacts. So why, even though there's all these distributed impacts, why does the regulated stream still get all the attention? And I think what it comes down to is this thing called the saliency bias. This is just pet theory of mine. And since I've got a soapbox, I'll tell you all about it. It was first mentioned in a paper about small lakes, actually, by Downing in 2010. The human mind tends to attribute causes of events or problems to the most obvious aspects of the system. So the saliency bias has been known by psychologists for years, but it's only recently appeared in the literature around water. To give you a really classic example of the saliency bias, which we all know and love, who's seen this little nugget? Carbon dioxide only represents 0.04% of the atmosphere. That's too small to warm up the planet. Who's heard that in the popular media? Quick show of hands, have we heard that? And does it make people spit when they hear it? Yep. Who would agree that that statement is silly? Yep, lots of nods around the room. You are correct, it's silly. But why? Why is it silly? The reason is 0.04% of the atmosphere is completely uncorrelated with risk. It has nothing to do with the level of risk that carbon dioxide presents. If that percentage of the atmosphere was sarin gas, we'd all be dead, right? So clearly percentage of the atmosphere has nothing to do with it. So that makes it a pretty ludicrous statement. So how about this one? Small dams represent 7% of storage in the Murray-Darling Basin. So that's too small to cause an environmental problem. Is that silly? Don't know. We actually, until I did this research, we actually didn't know the answer to that. It could be. So it all depends on whether or not percentage of storage is correlated with risk. Is that a reasonable sort of statistic to use as a proxy for risk, for environmental risk? that has become the core of my first research question, is that issue of, well, we continually ignore these unregulated streams and sort of forget about all the threats that are going on. Is that legitimate? And as statements like this about that, reducing things to simply their capacity or their annual volume, is that a reasonable proxy for risk? So, first question, as I said, saliency bias. What is the relative role of small dams compared to large in-stream dams? So that's the approach I've taken. I said, well, let's look at all these small dams and compare them to large dams and compare what sort of stress they're causing to biodiversity. Second problem is, as I said before, unregulated streams don't get a whole lot of attention. Certainly the regulated streams tend to get a lot more attention in the scientific literature and in government reports and so forth. And there isn't a whole lot of monitoring. And so quite often, if you're trying to do a study in a small stream, getting the data, just physically getting the data can be really challenging. And to do an ecological study, it's quite important to try to try to get hold of daily flow data. I'll explain why a little bit later, but daily data is really important, and that's really hard to get in a lot of places. So is it possible to get by with a longer time step, with monthly? And can monthly data tell us anything meaningful about ecosystems and ecosystem response? The third question, in unregulated streams, just because we haven't studied them much, we actually don't know which threats are the biggest ones. If you look across the world and look at large rivers, globally, there's plenty of papers, and they all say that large dams are a big source of a big threat to biodiversity. But what about the smaller streams where there are no dams? Now what? We actually don't. There's not a lot of information out there to allow us to compare different threats going on in these streams. What's happening in these streams, and how does it all add up? Is climate change big? Is climate change small? Are there things which are comparable to? We know climate change is going to have a big effect. Are there things which are going to be comparable to that? I've taken very much a practical sort of management approach to this question, and I've sort of asked a secondary question: can we use the information about comparing threats to mitigate climate change impacts? Which is a bit more of a sort of a proactive management question, but it's a useful angle. So, first question. I promised some of the technical stuff, so let's jump into it. First question was actually published as a paper in, what was it? There's so many Frontiers journals. Which one's this? Frontiers in Ecology and Environment, back in 2022. So to explain what I've done with this, how I've approached this first question, I've got to hit you with two big ideas, and you need to accept those ideas just for the next 10 minutes, okay? So roll with it for a moment. Big idea number one. That's a lovely little mountain stream, quite a small stream, it's clearly a mountain sort of environment. And that is a large lowland river. I'm pretty sure that's the Murray in South Australia. And so the big idea here is that those two streams are equally valuable. Now, what I mean by equally valuable is if you have a dam or an extraction and it's affecting 10 kilometres of small mountain stream, that's just as big a problem as a dam affecting 10 kilometres of lowland river. So what we're saying is 10 kilometres of mountain stream habitat is equally valuable to 10 kilometres of lowland river habitat. That's just one way to look at it. So that's the big idea. Those two types of streams are equal in terms of their length. What that means is that you can actually measure the impact of a dam in terms of its effect on the kilometres of stream that it affects. Yeah? Second big idea. Second big idea is all about the degree of regulation. This is a statistic which gets used, it's been used a few times in papers over the years. It's pretty simple. This is a little example. So if you have a little stream here, you've got a stream and a catchment, and there's all these little tiny itty bitty dams, or you could have one large dam, either way. The degree of regulation is simply the volume of those dams, in this case is 0.6 gigs, divided by the mean annual flow, which is 5 gigalitres a year. So 0.6 divided by 5 is 12%. So what you're saying is these little dams here represent 12% of mean annual flow. Does that make sense to everyone? It's just a matter of what's the capacity of the dams compared to the yield of the catchment. And the big idea I need you to swallow for the moment is that if the degree of regulation is above about roughly 17%, that's bad. Now, when I say bad, I should add that's a really arbitrary number. I wouldn't be brave enough to put a number like that on paper, but somebody else did it. That's from a paper by Grill et al. 2019. So they put down the number, I've just used it. It's completely arbitrary, but it's not a bad number. I'd have put the similar number somewhere between about 5 and 30%. So 17%, okay. When I say bad, if the degree of regulation is above 17%, what we mean is that there is a risk that dams in the catchment could be affecting the flow regime, which could affect the habitat in the stream and therefore affect biodiversity. So there's a risk. It doesn't mean the dams will definitely have an effect. It just means there is a risk present. So with those two ideas, degree of regulation above 17% is bad, and all streams are equal in terms of the value of their habitat. I then set about measuring the degree of regulation across the entire Murray-Darling and across the Arkansas River in the US. This is, excuse me, this is the Murray-Darling. And all of these orange dots you can see, all of the orange dots are the big dams, bigger than a gigalitre, so they're the really large ones. And that haze of blue in the background, that's all the little tiny dams. So the little tiny ones, what we're talking about is when you go for a drive in the country and you see all the little tiny dams in the corner of paddocks or beside the road, those dams, that's that haze of blue in the background. Some of them are bigger than that, but a lot of them are really small. So if we just go with the orange dots for now, go with the major dams and map out which streams in the Murray-Darling Basin have a degree of regulation over 17%, just as a result of those large dams. It looks like that. And anyone who knows the Murray-Darling will recognise the major river system there, the Murray and the Darling, Goulburn, Murrumbidgee. They're all quite familiar. Now, if I was talking before about the saliency bias and how it's easy to imagine that the large dams are responsible for most of the problems in a catchment. If that's the case, if we then add in all the small dams into the catchment, into this analysis, the major dams are 93% of storage. The small dams are only 7%. So if we add in just a little bit of extra storage, the story is going to be much the same. We should see much the same picture. The same rivers will be threatened. The same rivers will be at risk. But what happens when we put in the small dams? Suddenly half the basin lights up. This is, it's gone from 10% of streams in the Murray-Darling to 37%. So this means that 7% of storage in the Murray-Darling is increasing the amount of habitat affected by a factor of between 3 and 4. So it's having a huge effect on the length of stream habitat affected. So what we can say from this is categorically, the volume of a storage is not correlated to its risk to the environment. And that's a really important concept. The volume of the storage is not correlated to risk. If anything, it's the other way around. The small storages appear to actually have a greater risk. And that's got some really important implications for, this is a good basin to consider. You know, the Murray-Darling Basin Plan, a large part of the basin plan is focused on volumes of water, and it's focused on major rivers, and it's focused on major storages and a handful of icon sites on those rivers. Whereas what we're saying here is actually there's a huge amount of streams outside of that which are at risk. And the basin plan, I mean, there's a little bit of attention to that sort of thing, but not a lot. It's a small proportion of what it attends to. So you'd have to think, should we be reconsidering environmental management plans like that, which focus on only large rivers and large dams? There might be a need to reconsider those sorts of plans. Next question. So question 2 was about what can you do with monthly data? If you want to do an ecological study in a stream and you don't have daily data, it's actually really important to have daily data. This is an example of a flow series from this is the Delatite River in central Victoria. And I've just totally made up, these are the, I guess the notes there are the different ways that ecosystems can respond to the flow regime. So you could have this little section here where there's a long dry spell. The fish can't move between the pools because the water level's too low for them to move around. It's warm. There's not much flow. It could start getting pretty scungy. So fish and frogs and bugs could be pretty unhappy. There's some freshers in the sequence there. That could be really important signals for the biota to either move or to breed. And there's a couple of high flows in the middle of the year, which could be really good for inundating trees, could be really good for engaging lateral engagement with floodplains. And the really big flows are really good to sort of scour the habitat, rearrange the substrate and things like that. It just livens up the habitat. So different flows have different effects on the ecosystems. And these signals are different for every single stream, every single species. So it's all very complex, but you kind of get the idea. There's different flows which do different things. Now, we're all scientists and engineers, and so the natural response is to go measuring these things. So we measure things like what's the frequency and duration of low flow events, and then we try to link that to how has the ecosystem responded to that. What's the frequency and duration of high flow events? And then link that to ecosystem response. So there's been a lot of research over the years, and ecologists and hydrologists have been very, very creative. They've been very busy. And there's now more than 1,000 possible indicators to choose from. The list is enormous. I've just given a few very basic examples here, such as the timing of the annual maximum, long-term mean, long-term median, so forth. As I say, there's like 1,000 to choose from. It's a bit overwhelming. And there's plenty of literature which links these sorts of flow components to ecosystem response. But the majority of that research has been done using daily flow data. What's the daily flow tell us? And then how does the ecosystem respond? What if you don't have daily flow? If you don't have daily flow, it makes it very difficult to tap into that research and to use that research to say something about ecological response. So if you've only got monthly data, you've only got this sort of blocky sequence here. And you can see that if you move to monthly, you're missing a lot of data. A lot of things are lost. Things like you can see there was 3 low flow events, and that's just completely lost. It now just looks like one long low flow event. The existence of this little peak flow here has disappeared out of the flow sequence. These late freshers just don't appear in the monthly sequence anymore. And more subtle things like the exact shape of the hydrograph. Could I ask you just to make a mental note, just to keep an eye on the shape of that hydrograph and think about that. The rate of rise and the rate of fall. Now in the monthly data, that's completely lost. That's just completely absent. So it looks visually like we have lost a huge amount of information. But have we? So I set up an analysis to try to test this and try to work out how much information is lost. So to do that, I set up 2 blocks of data, and you can see these are the 2 blocks. First of all, I had a whole bunch of sites across Australia, and I calculated a bunch of flow statistics based on daily flows. So these are things like the examples here, mean daily flow, median daily flow, and all sorts of statistics using those daily flows. I then translated those translated each of the statistics, where possible, to a sort of monthly equivalent. So mean daily gets translated to mean monthly, etc. So they don't all translate, but many of them do. So I translated wherever I could to a sort of a monthly time step. So it gives us 2 blocks of data. So the 2 blocks of data, I had 467, the data has 467 rows for 467 sites using the Bureau of Met hydrologic reference stations. The daily flow statistics was 171, but only 115 sort of made sense to translate to a monthly time step. So the question I was trying to answer, can we estimate the daily flow statistics if we only had the monthly ones? And that's, I'm sure you'll notice, that's a sort of a regression and prediction type of problem. The bigger question is, I guess at a more philosophical level, how much daily flow information actually is within that monthly data? If we only had monthly, how much of the daily flow information is still contained in there? Now, it's a regression problem, it's a prediction problem. Unfortunately, both the daily and monthly data sets are absolutely riddled with redundancy. So just the first 2 columns are a great example of redundancy. You've got the mean daily flow and median daily flow. Huge correlation between the two. And as soon as you have correlations like that between columns, you have redundancy, and that means multivariate analysis like regression will tend to fall over. And there's so much redundancy in this data set, regression was simply not an option. So I had to come up with another solution which dealt with the redundancy first. What I came up with is a thing called partial least squares regression. Really great technique. And it deals with the redundancy in the data sets and then does the regression and prediction all in one step. It's pretty amazing. And I came up with this lovely slide, thought long and hard about how to explain it. And I came up with this lovely slide and decided you guys don't actually need to know any of this. It just blew my mind. It was just far too complicated. So what you need to know is that partial least squares regression is the evil love child of principal components and regression. And when I say evil love child, maybe this is just my experience of the Python library I was using, but it's a bit like a grumpy teenager. It was difficult to communicate with, frequently needed to be coerced, very emotional. So it was a little bit challenging to use, but we got there in the end. Does it work? A simple answer is yes. I was actually really amazed how well it works once I got through the emotion of using the library. Now I'm going to have to explain a little bit here because this is a little bit complicated. This is a simple plot showing R squared. So the higher the R squared, the better the prediction. These are indicator categories. So the little, this is a cheat sheet down the bottom here. This table here is a cheat sheet to help you understand what these codes mean. So MA refers to the magnitude of annual flows. So any statistics which relates to the magnitude of annual flows is dropped into this category. There's one down here which is DH, that's the duration of high flows. So those statistics are all bunched together. So you can see there's sort of different categories of statistics, and each cross here represents one statistic. And what's the R squared? How well can we predict that statistic across the whole of Australia? And you can see most statistics of the 171 I had, I could actually predict most of them better than sort of 0.6 or 0.7. So that's a pretty good R squared. It's not great, but it's pretty good. There were a few surprises in there. Things like the frequency of low flows and the frequency of high flows, they tend to be very short-term events. So especially high flows, they only last, a high flow event might only last for a few days. So predicting the frequency and duration of those events with monthly data is challenging. So some of that information just is lost. However, this category down the bottom here, RA. So that's the rates of rise and fall. Effectively, these little crosses here are statistics which represent the shape of the daily flow hydrograph, the rate of rise of the rising limb and the falling limb. And most of those statistics we can estimate with an R-squared of better than 0.8. There is no monthly equivalent for those statistics. You can't calculate, I mean, I guess you could calculate the rate of rise of monthly flows, but that kind of doesn't make a lot of sense. It's not a very helpful statistic. But the daily flow information is still there, reasonably predictable, which really did surprise me. A lot of that information is still there. So this is a map showing the model error, so RMSE, so that's overall error. So the higher numbers are the red dots, and that's where you've got higher error. So your model is not working so well. And you can see it's not working so well across Central Australia and across the Northwest. But you can see the vast majority of sites, just the sheer weight of numbers, is down the East Coast. So it's not too surprising if you train a model down the East Coast of Australia. Funnily enough, the model is not going to work so well in the Northwest or across Central Australia, where flow regimes are utterly different. So that's not too surprising. But across down the East Coast, and for the majority of sites, it actually works really well. Overall, we found that monthly flow data contains about 85% of daily flow information, which is remarkable. A lot of these statistics that I was using are the statistics you would use to make ecological inferences. And you can, and the variability in those stats is 85% of the daily variability is present in monthly data. What that means is if you're doing an ecological study, you can get away with monthly data. Certainly as a first pass, it's perfectly acceptable to use a rainfall runoff model, generate monthly flows, or use the outputs of a monthly water resource model, for example. Monthly time step is okay. There are ways you can use that monthly data to tell you something about the daily flow regime. So not having daily data is not as big an obstacle as we might have thought. It's a problem, but it's a manageable obstacle. Okay, question 3. Now, I've submitted this paper. It's been a couple of months, but Journal of Hydrology haven't got back to me yet, and I gather that's normal. So I guess the question here, just as a reminder, is we know there are threats in unregulated streams. We know there are things which affect the flow regime, but we don't really know how they compare. The available literature gives us no clues as to how these things compare. Which ones are big, which ones are small, which ones do we need to worry about? So I set up a modelling framework just to deal with these 3 threats: climate change, small dams and small extractions, and that's across Victoria. So there are others that I could have included, but these are the ones where the data was available and the modelling is tractable. Things like plantations, I don't think the modelling is quite. I could have put in plantations. That's a genuine problem in many small streams, but I'm not sure the modelling is quite ready for a monthly time step yet. And there are other threats which you could include if we could find a way to do the modelling. But these are the 3 I've modelled just for the moment. So how did I set up a hydrological model to do this? It was a customized model. So I've built this specifically for this particular piece of research. The first step is I've got these, I think it's just over 500 sites across Victoria. And at each site, I had enough data to calibrate a rainfall runoff model. And the rainfall runoff model represented the flow at each site if there were no dams and no extractions. So that rainfall runoff model is calibrated. I don't like to use the word natural because that means different things to different people, but a lot of people would call that natural. I call it unimpacted. It's got no effect from dams, no effect from extractions. So the rainfall runoff model is calibrated. So you put in rainfall and evaporation, you run the model, you get flow. I'm sure we've all done that. That's all fairly familiar. As a second step, I then bolted on a small dam model. So I said, well, let's take the output of the rainfall runoff model and then let farm dams. Let's get all those small dams and they can take their cut. And then let's see what's the flow downstream of that. As a third step, I then said, well, what are the small extractions in the system? Let's run the rainfall runoff model. Then farm dams can take their cut, and then small extractions can get their cut out of because they tend to be further downstream. And then what's the flow downstream of the small extractions? So that's 2 out of 3 threats. That's small dams and small extractions. The third threat is climate change, and that was a little bit more challenging. To represent the effect of climate change, I've actually gone and changed the input rainfall and evap. So you have to change, and I've used Victorian Climate Projections 2019, which provides a lot of good delta change information on across Victoria. And I know there are limitations associated with the use of delta change and the use of a historic sequence to represent the future. Aware of all that, but this really represents an initial estimate of just how does climate change compare? What kinds of effects could we expect? Is this even a thing? Should we even research this any further? So as a first cut, I know there are limitations, but it's complete. I still think it's a completely reasonable choice. So I've applied from the Victorian Climate Projections 2019. There were, I think, 6 GCMs. So I've got an ensemble of 6 GCMs and a number of different time horizons and RCPs, all that kind of thing. You change the rainfall and evap, and that changes the runoff from the catchment, and that can flow through to different impacts from small dams and different impacts from small extractions. So this model is really nifty because what it allows you to do is actually switch on or off different components. You don't have to run the climate change component of that. You don't have to switch on the farm dams. You don't have to switch on small extractions. You can put them on one at a time or in combination. So this is the sort of thing that comes out of it. Let's just start by looking at some of the highest flows up here. This is a catchment. This is the mean monthly flows for Axe Creek. So this is just near Bendigo in central Victoria. The solid black line here, the heavy black line, that's the unimpacted flow. So that's, as I say, I don't like to use the word natural, but it's natural-ish. It's the flow without any extractions or impoundments. The line just below that is what's happening now, effectively. That's the flow with existing small dams and with existing extractions. That's where we are now. This grey envelope down here with the median showing through the middle, that's the envelope of what would happen if we just let climate change rip. Let's leave all the small dams there. Let's leave all the small extractions. Everybody can take what they like and just let climate change happen. That's the envelope of the main monthly flows for this catchment. And as you can see, the impact of climate change compared to the impact of small dams and extractions, it's like an order of magnitude higher. It's so much larger. And that's really useful information to know that climate change is an order of magnitude bigger than anything else that's going on. However, that's just in winter. Let's just swap focus to summer over here. And suddenly the story is really different. You can see that the impact of, you can see the unimpacted flow, and you can see the impact of dams and extractions. Climate change, the envelope is actually pretty similar to what we've got now. So in this catchment, if you manage the impacts of all the dams and manage the impacts of all the extractions during summer to try to minimize their effect, you would find that you can actually mitigate the effects of climate change. You can actually bring the stream back to where it was without climate change. And that's a remarkable outcome, that we can actually manage what we're doing in the stream and mitigate the effect of climate change. That's really surprising. Let's have a look at the whole of Victoria. Now, I'm going to need to explain some of the colours in this. There's so much information to unpack, so bear with me a moment. There's three scenarios here. You can see the three columns. The first scenario here is just what's happening now. What's the effect of existing dams and extractions? The next column is what happens if we just let climate change happen and don't do anything with existing users. The third column is, well, what happens if we manage existing dams and manage existing extractions to try to minimise their effect? That could involve getting rid of them, could involve fitting bypasses. There's all sorts of options, but minimise their effect on the flow regime. And the two rows here is what happens to the mean February flow and mean August flow. So in the first one, you can see some red colours here. So that the red colours, on the scale over here, this is a stress score. So once we get down to -1, what that means is the mean February flow is 100%. 100% of the time is outside its natural range. It has shifted so low that it's completely outside its natural range. That's a score of -1. What we can see here, there's no -1s, but there's a few sort of -0.2 to 0.5. So that means there's quite a few catchments. Just with the existing dams and existing extractions, the February flow is now, out of all the Februaries, 20 to 50% of them are outside the natural range, which is a bit of a concern. And if we let climate change happen, it gets so much worse. You can see there's a lot more red going on in here. Some of the catchments are even more than February's 50% outside its natural range. But the interesting thing is, what happens if we then go and manage the existing dams and extractions? If we manage them, we can you can visually see there is an improvement. There is a real improvement in a lot of catchments. And that's telling us that by managing dams, managing extractions, we can actually mitigate the effects of climate change in summer in quite a lot of places. Shifting to mean August flow, so looking at winter, you can see there's almost no red there, which means that the effect of existing dams and extractions is doing nothing to winter flows pretty much. And as we saw before, the effect of climate change is like an order of magnitude bigger than anything else during winter. So that's not too surprising. As soon as climate change happens, wow, this is the ensemble mean of all the GCMs. So some of them are worse than others, but the ensemble mean looks pretty scary. August flows, of all the Augusts, 50% of them are outside the natural range. And that's going to have a really profound ecological effect. That loss of flow will just make a big change to a lot of ecosystems. That's a consistent change across a lot of years. And looking at the last scenario, if we manage small dams and extractions, there's almost no change. There's a couple of little blips, a couple of little changes here and there, but basically the story is very much the same. And what that tells us is that managing dams and extractions will have pretty much no effect on winter flows. So mean August flows unaffected. The summary is that we can mitigate the effects of climate change, but only in one season. And it remains a moot point whether that's actually worth doing. I personally think it is, but that's still something to be discussed with waterway managers. That's a tricky problem because if you manage one season, there might be fish that are depending on a particular flow happening in winter. So why are you protecting their summer flows if they're going to die anyway because they don't get their winter flows? It's a tricky problem, but if you can do something, I figure we should be doing something because there's going to be lots of other things outside the flow regime affecting these ecosystems. We should be doing something. So this is actually a really profound result because I set up this analysis to look specifically at different parts of the flow regime. If I'd simply looked at the mean annual flow, I'd have got that bottom line there because mean annual flow is strongly correlated with August flow. So I'd have got that bottom line there. And the answer would have been, no, we can't mitigate climate change at all. Climate change is far and away the biggest threat. But because I've separated it out into different components of the flow regime, suddenly this policy option has appeared. And we had no idea that option was even plausible before. And now it's a genuine option. We can see it there. But only because we've separated out those parts of the flow regime and also run the analysis to separate out the different threats and assess them individually. So that's really important to do that and to think about the whole flow regime, not just mean annual flow. Ooh, nearly there, folks. Some conclusions. So the first question, what's the relative role of small dams compared to large? Small dams affect 300 to 400% more habitat than big dams. We got much the same result for the Arkansas River basin in the US. It was sort of like, I think it was close to 300%. So that's a huge result. These small dams are affecting so much, the enormous length of waterways, enormous amount of habitat, far more than large dams. And does make you wonder if we should rethink how we go about managing large river basins. Should we be focusing on the large dams and the large rivers and icon sites, or should we be focusing some of the smaller streams and protecting what we can and protecting the longer length of habitat, protecting more habitat rather than the big rivers? Can monthly flow data tell us anything meaningful about daily flow data? Yes, it can. There's a method here. We can use it. 85% of daily flow information is in the monthly data, so there's no reason not to use monthly. And that's really useful because that still allows us to tap into all the existing flow ecology research, which uses that daily data to make inferences about how ecosystems might respond. We can still tap into that, even if we've got monthly data. That's a really important step. And how does climate change compare with other threats? Turns out that if you're just looking at mean annual flows, yeah, climate change is an order of magnitude bigger than anything else going on in unregulated streams, or certainly anything else that I was examining. But turns out that if you separate out the impacts a little bit, you find that the summer impacts, we can actually mitigate those. Just by managing the existing users, we can actually have a genuine positive effect in summer. And that's a really important conclusion. That's a policy option we just didn't know about before. Yes. He is done. So thank you to everyone for coming along today. And nobody threw any tomatoes. That's fantastic. Nobody heckled. That's great.
Question time, yeah.
Oh, yeah. Okay, maybe the rotten tomatoes come later. Couple of thank yous. Thank you to my supervisors for being so patient. I know the pace of my work was painfully slow, glacial. So thank you for your calm patience. Thanks to, if anybody gets the chance to work with Julian Alden at University of Washington, he's an awesome guy. So big thanks to him. He was co-author on 2 papers, and I think his input really lifted those papers from being good to being really schmick, to being really, really excellent. So really appreciate his input. And thank you to my partner, Catherine, for putting up with me doing all of this for years. After all that ranting and talking about this stuff for years, she's still willing to have me in the house, which is amazing. And thank you to my son, Reese. He keeps providing me the motivation to do this stuff. He has this completely, his enthusiasm for learning and learning new and interesting stuff just seems to be unlimited. He just wants to learn new things all the time. And really that's what it's all about. So that's really good motivation for me to keep doing this stuff. And if I can just break with tradition for a moment, I know at the end of these talks you normally say thank you to everybody, but if I could express just one short regret that my mum couldn't listen in today. She's very sick, couldn't listen in. She was a primary school teacher for 40 years, I think, and she always said education is an investment that you can never take away. And I think she'd have been really stoked to see me standing here for an hour rabbiting on. So thanks very much, everybody. And I think we've got time for some questions. I will start first with people on the floor here, and then I'll ask some folks online if anybody wants to ask a question. I'll just get this microphone working. Oh, working.
Thanks, Rob. Thanks, Rob. That was great. I have a question about research question 2, and you said like you could predict using monthly data the rise and fall indicators, but you said there's no monthly equivalent. Did you look in your, like you did your principal component regression, you could look at the principal components that allowed you to predict the rise and fall variables? Like what pieces of data were giving you information about that in the end? Did you look into that?
About the rise and fall?
Yeah.
It's really mixed. It's information about things like the rise and fall and things like the duration of low flow events, which you'd think is lost. It seems to come from everywhere. And it's more about the signature of, the way I think about it is there are processes going on upstream. In the end, what we're seeing in the stream flow is just an expression of those processes, and just one small expression of those processes. All we're seeing is the flow above the riverbed at some point downstream. There are a lot of those processes which affect more than just the flow. They could affect, it could be the terrain in the catchment is forcing a particular shape of the hydrograph, but the terrain in the catchment may also force a particular peak flow compared to the mean, or might be influential in the range of high to low flows year to year. And so some of those statistics, which seem to have nothing to do with the hydrograph, are actually related. I did actually look, and I've given a few examples of those in my paper, and all the correlations are there. So you can actually look through and see what's driving some of the prediction. And it doesn't make much sense at first, but when you think about a catchment that has the signature of, it might have this particular shape and this particular predictability of flows, it does tend to lend itself to a particular shape of hydrograph. So yeah. Anyone else? Any other questions?
Thank you, Rob. Research question 3.
Yep.
You magically calibrated a model to unimpacted catchments. How?
I said, Murray, no heckling. So how did I calibrate that? So there was a large project done for the Victorian government in 2004 and again in 2012, where a lot of those flows were calculated largely based on gauge data, sometimes based on water resource models, which in turn were from gauge data, and a lot of modelling to remove the effect of large dams like Eildon or Glen Maggie, a lot of large reservoirs. And we had, so we did have some calibration information, and we've calibrated as well as we can to that data. Does that answer the question?
Yeah.
Cool. Anyone online want to fire a question?
Yeah, there's a question in the chat, Rob,
Oh,
if you're able to view it.
oh, the technology.
Or I could read it to you.
Oh, why did you exclude parts of northwest Victoria in the hydrological modelling? So yeah, basically there's not a lot of runoff. So yeah, I'll just zoom back a little bit. Yeah, you can see parts of northwest Victoria. Parts of the Wimmera and so forth, there's actually not a lot of stream gauging, and what there is highly unreliable. And I also have concerns about a lot of, certainly parts of northern Victoria, even where there are gauges shown there, the terrain is so flat. I do worry about hydrological connectivity. Parts of around Kerrang and so forth, right, those areas of northern Victoria, the terrain is less than 1 in 400, sort of 1 in 500 or so, really, really flat. If it rains on that area, the water there, in most cases, would never make it to a river. So if somebody intercepts that water and puts it in a dam, you're not really affecting the stream flow because that water never would have made it anyway. So there's a hydrological connectivity problem. So I'm very nervous about including catchments in those really flat areas or where there's very low runoff. Any other questions online?
I think we're coming right up till 12 o'clock, so we,
Ah, where is the mouse gone? There it is. Ah, did I try PLSR using it on the catchments in Northern Australia? Yes, I did. Actually, that's a really great question. That's actually in the paper. I had a go at, I think you can see from, oops, from that map. Yeah, there's inland and northwest. Inland and northwest areas are not so good. And so I did try calibrating a model to those areas and particularly to flow regimes which fit into that category. I used a classification system to sort of classify the flow regimes, and I picked some of those which didn't work so well. The model just didn't improve. And I think the fundamental problem is the suite of indicators I was using is really designed for Northern America and Europe. It's this strange sort of grab bag of statistics. It's not really suited to the Pilbara, you know, and so it's not surprising that those statistics don't describe the flow regime very well. And so the model just tends to fall apart.
all right, we might wrap up given the time. Thank you very much, Rob. And yeah, thank you for working with us through the PhD. So Rob is aiming to speak very soon in the next couple of weeks, so we'll be celebrating.
Awesome. Okay, thanks everyone.